Covalent bonding, part 3. In this video we're going to talk about the two methods that can be used to identify the type of bonding that happens between atoms. Let's start out by considering a very important property of elements called electronegativity. Electronegativity is defined as the attraction that an atom has for bonding electrons. An atom with big electronegativity has big attraction for bonding electrons. An atom with small electronegativity has small attraction for bonding electrons. So what are bonding electrons? Well, those would be the valence electrons around an atom's nucleus, and the valence electrons around some other atom's nucleus as well that might get involved in the bond. It's the attraction for any electrons that would be involved in bonding. Now remember, the valence electrons are the outermost s and p sublevel electrons. Electronegativity is not an observed value, it's a calculated value. It could be on a low end of 0 to a high end of 4. It's a pretty small range of numbers. And lucky for us, electronegativity values have been calculated for the elements already. We don't have to worry about how to do that calculation. And those electronegativity values are written down here on this periodic table of electronegativities. Now you can see that the elements down in the lower left here have the lowest electronegativities. Notice that FR is 0.7. And the elements over here in the upper right have the biggest electronegativities. Notice that F is 4.0. Now you might say, well, what about these noble gases? They don't have an electronegativity value. Well, that's because electronegativity isn't really applied to noble gases since they don't typically bond. So what we can say in general is that as we go up and as we go to the right on the periodic table, we see that electronegativity gets bigger. Now there are some elements that go against that trend, but the general trend is that up and to the right is bigger electronegativity. Well, that means the elements that are down here, and if you see this bold zigzag line, remember that's the dividing line that divides the metals from the nonmetals. Now there are some metalloids or semi-metals along that line, but for the purposes of identifying bond type, let's just say that all of the elements to the left are metals and to the right are nonmetals. So metals typically have low electronegativity and nonmetals typically have high electronegativity. So what can we do with that knowledge? Well, let's say we're going to use M to symbolize metal, and they have low electronegativity, and M to symbolize nonmetal, they have high electronegativity. And when we need to, we'll take a look at the periodic table of electronegativities to look up the electronegativity value for any particular element. The first method of identifying the bond type that happens between atoms is a qualitative method. Now you might remember that we've used the term qualitative and quantitative before when we were talking about observations. Qualitative describes something that is characterized without a number. So we're describing it by its quality. Whereas quantitative is characterizing something using a number. So if I say, hey, look at that guy, he's very tall, that's a quality. If I say, look at that guy, 7 feet tall, because there's a number there, that's a quantity. So using the qualitative method, we can take a look at the type of elements that we have, whether they're metals or nonmetals, and predict the type of bonding that would most likely occur. Remember that metals have low electronegativity, low attraction for bonding electrons. So if you have a metal and another metal combining, what's going to happen is the valence electrons will keep passing back and forth between the metals. We'll get an effect called the sea of valence electrons, and the bond type is metallic bonding. And if you remember from some previous videos, metallic bonding and the sea of valence electrons theory explains why metals have their 4 properties. Now, if you have a metal with low electronegativity, low attraction for bonding electrons, combining with a nonmetal, which has high electronegativity, high attraction for bonding electrons, what's going to happen is the metal is going to lose its electrons. They'll be transferred over to the nonmetal. The metal will form a positive ion, and the nonmetal will form a negative ion after those electrons transfer. and the positive and negative ions stick together because opposites attract, and we have an ionic bond that forms. Now, our other possibility is that we have a nonmetal with high electronegativity, high attraction for bonding electrons, and another nonmetal also with high electronegativity, high attraction for bonding electrons. Well, neither one of these atoms is willing to give up the valence electrons or the bonding electrons, so they share them and they form a covalent bond. So identifying bond type qualitatively is relatively simple. We just need to look at a periodic table to determine whether the elements involved are metals or nonmetals. So let's consider bronze. Bronze is a metal that's made with copper and tin. Cu copper, Sn is tin. Cu is right there on the periodic table. Well, that's definitely a metal. It's to the left of that zigzag line. And Sn is right here. And that's also a metal to the left of that zigzag line. So we would say that when we have a metal and a metal, we have metallic bonding. And in fact, bronze can really be considered to be an alloy, a mixture of those two elements, more than it could be considered to be a covalent compound or any kind of a bond. Now, it is possible that some metals, relatively rarely, can actually form covalent bonds by sharing electrons. And then we would call those intermetallic compounds. But for the most part, when you combine two metals together, we get a mixture of the metals. And a homogeneous mixture of solids like that, solid metals, is called an alloy. So bronze is an alloy. Now let's consider this compound, calcium fluoride. Notice that calcium, Ca, is way over here on the left. It's a metal. And fluorine, for fluoride, is right there, F. It's a nonmetal. So when we have a metal combining with a nonmetal, the metal's low electronegativity, low attraction for bonding electrons. Nonmetal is high electronegativity, high attraction for bonding electrons. We're going to see the electrons transfer from the metal to the nonmetal. The metal loses electrons and forms a positive ion. The nonmetal gains electrons and forms a negative ion. We're going to get ionic bonding. And that's going to result almost always in a crystal or a repeating shape of ions. So we'll get some solid ionic crystal that forms from that. Let's take a look at a third example, boron trichloride, or BCl3. Notice that boron is on the right-hand side of the zigzag line, and so is chlorine. So they're both nonmetals. So if you have a nonmetal with high electronegativity and another nonmetal with high electronegativity, what we're going to see happen there is that they both pull on the bonding electrons. So when they bond to each other, they share those valence electrons, and we're going to get covalent bonding. As a result, we'll get a single piece of BCl3 called a molecule. The term culimole means little lump if you translate it from Latin. So we get a little piece of that BCl3, a molecule of it. Now that's the qualitative method. Let's consider a quantitative method, a method that considers electronegativities with the numbers involved, with the quantities involved. So what we can do is find the electronegativity difference between two elements that might bond to each other. Remember that when you do a difference calculation in math, you have to subtract two numbers. So we're going to take electronegativity values for elements and subtract them. If when you subtract the electronegativity values for elements, the difference is greater than 1.67, we would say the bond is ionic. So one atom would have a lower electronegativity than the other by a difference that's greater than 1.67. Now you might see numbers that are slightly different than that in different sources, but we can stick with that one. Now if you have a difference that's greater than 0, so there's some difference in the electronegativities, but less than 1.67, we could say that we're going to find a polar covalent bond forms. Polar covalent is a bond where there are electrons that are being shared unequally. So we get one end of the molecule that's slightly negative, we call that the negative dipole, and one end of the molecule that's slightly positive, that's the positive dipole. So very much like the north and south poles of a magnet, or the north and south poles on the Earth that are somewhat associated with the magnetic field, we could say that a polar covalent molecule is going to have a little uneven distribution of electrons because of this sharing that's uneven or unequal. Now, if you have two elements that have zero electronegativity difference, now if you subtract two numbers and they have zero difference, that means those two numbers are the same. That means they're going to share the valence electrons equally, and we get what's called a nonpolar covalent bond. Let's take a look at some examples. And we're going to have to use our periodic table of electronegativities to look up some electronegativity values here. This is examples, or these are examples of the quantitative method of determining bond type. If we have Ca bonded to F, Ca has an electronegativity of 1.0, and we can see that it's written right here, 1.0 on our periodic table of electronegativities, and F is 4.0. So we always take the big number minus the small number. So 4.0 minus 1.0 is 3.0. Now you might say, hey, there are two fluorines there. Doesn't that matter? Well, no, because the calcium will bond to one fluorine on one end of the atom, and then it'll bond to another fluorine on the other end of the atom. So we can look at those as two separate bonds. So each of the bonds would be ionic bonds. Again, we have an electronegativity difference greater than 1.67 here. And when electronegativity differences are greater than 1.67, we're going to get ionic bonding. So that's the number you have to remember, 1.67. All right, let's consider Ci4. Now I know that there are 4 iodines, but carbon will be bonding to each of those iodines with a different bond. So here we have carbon with a 2.5 electronegativity, and iodine, I, also has a 2.5 electronegativity. So since the electronegativities of these two elements are exactly the same, the difference, 2.5 minus 2.5, is 0. 0 electronegativity difference indicates a nonpolar covalent bond. So we would say that Ci4 has bonds that are all nonpolar covalent. Now we don't have to worry about single or double or triple bonding. We just have to compare the type of the elements and compare the electronegativity of the different types of elements. Let's take a look at one more example, HCl. H has an electronegativity of 2.1, and Cl is 3.0. So we always take the big number minus the small number. 3.0 minus 2.1 is a difference of 0.9. When we have an electronegativity difference that's bigger than 0 but less than 1.67, like 0.9, then we get a polar covalent bond forming. So we can use a quantitative method to identify bond type as well. Let's talk a little bit about polarity, but first we should go over some Greek letters that are being used with polarity. Now you might recognize this triangle from math. Triangle is often used to symbolize the change in something, and this is uppercase delta in Greek. If you go through the Greek alphabet, you have letters that are pretty similar to the letters in our alphabet. So alpha, beta, gamma, delta. It's kind of like a capital D in our alphabet. If we write a triangle like that, delta is like a D in the Greek alphabet. And just like we have an uppercase D, we also have a lowercase d. So it looks like this in our alphabet. In the Greek alphabet, the lowercase d looks like a rounded D on the bottom with a little squiggle on the top. So that's lowercase delta. That would be lowercase delta. We have a little spelling error there. Lowercase delta. And that's in Greek. All right, so we can say that if we have a delta with a plus sign, that would indicate a positive dipole. Delta, right, for dipole. And if you have a delta with a negative sign, that would be a negative dipole. Now they always come in pairs, that's why we call them dipoles. And when we see that there's a delta charge like that, delta plus or delta minus, that would indicate that there's a fraction of an electric charge. So the electrons haven't transferred over and taken their entire charge with them from one atom to another. Because the electrons are being shared, but shared unequally, the charge that is formed there is not a complete positive or a complete negative. It's a fraction of a positive or a fraction of a negative. And you can actually calculate the size of the magnitude of the delta plus or delta minus. It would be some decimal value in every case. So we would say that polar covalent bonding is when electrons are shared unequally because the atoms have unequal electronegativities. So the electronegativity difference is bigger than 0 but not bigger than 1.67. We would say that one side of the bond would be delta plus and the other side of the bond would be delta minus. Nonpolar covalent bonding, on the other hand, is when electrons are shared equally because the two atoms have exactly the same electronegativities, and subtracting the electronegativities we get a difference of 0. When we see an electronegativity difference of 0 between two atoms, the nonpolar covalent bond would exhibit no dipoles, no delta plus or delta minus charges. We'll take a look at assigning delta plus and delta minus later on in a different video, but if you understand what we went through in this video, then you should be able to do this. For these 5 compounds, 1 through 5, you should be able to use the qualitative method to identify the type of bonding. So if it's a metal and metal, it would be a metallic bond. If it's a metal and a nonmetal, we'd see an ionic bond. And if it's a nonmetal and a nonmetal, we would see a covalent bond. And for 6 through 10, you should be able to use the quantitative method to identify the type of bonding, where we employ the electronegativity values and subtract the big value minus the small value to get a difference in electronegativities. So for these 5 compounds, if the difference in electronegativity is greater than 1.67, we have an ionic bond. If the difference of electronegativity is greater than 0 but less than 1.67, we have a polar covalent bond. And if the difference of electronegativity is 0, then we have a nonpolar covalent bond. So for the first 5, identify whether we have metallic, ionic, or covalent. And for the second 5, identify whether we have ionic, or polar covalent, or nonpolar covalent. So these two different methods give us slightly different information, and they're done slightly differently. Good luck!